接下来的这段演讲呢，我们邀请到来自荷兰的专家Mr. Erik Pekkeriet 来跟我们讲一下 Applying Robots in Agri-Food Cultivation.
Good, thank you very much. I was asked to tell you a little bit about robots in agri-food cultivation, so that's what I'm going to do. I'm working at Wageningen University and Research in the Netherlands, and I'm there the program manager agri-food robotics. This is our campus, and we have about 6,500 people working on agri-food. Perhaps you know that we are a very known university, so we are ranked #1 in agriculture and forestry. And here you see a few other rankings. And what I also like is we always take this ranking into account, that because of the ranking of Taiwan, we are also still #1 in agriculture. So I would like to thank you for that. So what is Wageningen University and Research? So the name already says it, it's university and research, and both entities are similar in size. So we have about 3,500 people working at the university, but also 3,500 people working at the research station. And the research station, that's where I'm also coming from, is more the project, the contract organization where we do projects for companies, some NGOs and some international governments. But Wageningen is not only Wageningen, so the heart of Wageningen is somewhere here, but we have many research stations spread over the Netherlands, and that's what you can see here. So Wageningen is a whole set of institutes where we also can grow on sand, on clay, on peat. We have all different kind of fields and areas to grow crops. So this is my team. So what is my team actually doing? Our expertise is laying in machine vision applications in the visible range with the geometric features in an image. So what do I see in the image? How many fruits? How ripe are the fruits? That's typically geometric features. But the spectral features can tell also something about the content of the fruits, the number of sugars. And so we also look in the spectral range and in internal features of the fruit. So from X-ray to terahertz, there's a lot of more information about pests and diseases, ripeness, taste, these kind of things, nutrient deficits. And that's what we also do. That's the spectral area. Then we have the robotic systems where we do also a lot of actuation. So both these three items will come back in my presentation. And what are our main markets, so to say? Where do we develop projects for? It's for breeding companies to make phenotyping tools. It's for precision farming, to measure everything on every square meter, so to say. It's for hands-free, to reduce labor by robotic operations, harvesting, packaging, these kind of operations. It's also post-harvest quality. So when a fruit is harvested, especially in the fresh, we are focusing a little bit more in the fresh than in the process. We do some processed food, but mostly it's about the fresh harvested products that needs to be stored, controlled, need to be checked throughout the value chain from harvest to export to retail. And in every stage you would like to check the quality, and we make equipment for that. And then the top four are more technical driven. The last one is about uptake of robotics. So what is required for farmers to adopt robotics, and what are the ethical and legal issues that are still hindering the uptake of robotics. And I will also come back to that later. So that's a little bit the field you are facing now, and I will start to give some input on the drivers for robotics. What we see, I take it of course from a Dutch perspective, but I'm quite sure that it's quite similar in Taiwan as well. In the Netherlands, we see definitely that we are very much depending on migrant workers. So a lot of the workforce that is doing the primary work, as I call it. So the harvesting, the picking, especially in horticulture. We use a lot of migrant workers from Poland, Belarus, Ukraine, Bulgaria, and Romania. But initially we only had Polish, and we see that to have enough workforce, we also now need people coming further away from the Netherlands. I think that's also quite similar what I see in China, for example, when we did some research about the Shanghai area. They also need to source their workers further and further into the country, and it's just simply difficult to find workers doing this kind of work. Another thing what we see is that the workers that come to the Netherlands are also getting older and older, which means that the younger age at the moment, they find better jobs in more IT-driven domains, so to say. So the IT-driven services, the industry or the society also needs a lot of jobs there, and they are consuming the younger people. So for the future, we have, I think, quite some problems to find labor. So that gives at least a little bit power and fuel for the robots. Another thing that is very important in the Netherlands, at least, is also the rural impact of agriculture. So with our big machines, we also have a high number of livestock as well. We have a big impact on our soil, on our nature, and especially in a crowded country like the Netherlands, there's a big push to grow more regenerative. So to have always a crop in your field and seed between that. So for example, if you go to a maize field now these days in the Netherlands, there will be always also a green fertilizer or a green crop covering the soil to give nitrogen to the soil. But it definitely changes a lot how we can harvest things, and they would like to enlarge that also to other crops, so that you have multiple crops in your field in a mixed cropping system or a strip cropping system of an inter-row cropping system. All these new cropping systems are very important now these days in the Netherlands, but there are no machines for it. So they are testing a lot, and there's a lot to do there also from the robotics part. I will go back to that later. So the biodiversity collapse, that's something which is very important in the Netherlands now these days. But then we have also a war, which also gives a new dynamic that also countries find food security very important, and that also gives some effect in what do we on the robotics part, because for example our migrant workers from Belarus disappeared. Luckily we had some migrant workers from Ukraine now, but they will also disappear, and what do we have then? So the war really affects the way how we produce food as well, and I think you all can see that. Then I would like to start with some learnings from precision farming. I will come to the robots later, but I think we have learned a lot from precision farming, and that's also something we need in robotics. So to be able to do precision farming in the Netherlands, which means that you handle every crop on every square meter in the best way, and you also apply specific treatments to the crop. And to be able to do that, you need quite some infrastructure, and that's also where robotics starts. So that's why I start. So I think it's always very important to have good GNSS signals on the farm, and luckily the Netherlands is fully covered with RTK GNSS systems, so we have 2 centimeter precision always available throughout the whole of the Netherlands, but that's not the case in all situations. Then you also need a basic sensor data setup. So Dutch farmers use crop, soil, weather sensors that can also be loaded into the farm management system. So that was the first touch. So you also need a good farm management system where you can combine different data streams. So data acquisition is one, because if you do not have data, then it will be very difficult also to do precision farming. Then models should run on these data, because only data, that's no information what to do. So you need also data processing and to support you in your decisions. So you need decision support modules. And then you can load these software algorithms into your machines, and you can do some variable rate applications. Of course, you need a good connection between the tractor and your implement. And in most cases, that's an isobus terminal. But still, a lot is missing in robots. So there's less, but it's really important that the implement uses also the sensors of the tractor or the power pack, so to say. And you need, of course, also precision actuators. So that's at least required to do some precision farming. And you need to follow the whole list to be able to find out if you are ready to join precision farming. And in the Netherlands, we did some research. So how are farmers ready for precision farming? And we learned that all farmers have a computer, close to 100%. They use the decision support, or they have access to decision support system. Doesn't mean that they use it, but they have access to decision support system, which they can load into their computer. They have digital crop recording, but they hardly use it. And they all have a smartphone or a tablet, where they also run agricultural modules. Well, this was 2019, and this is increased even in that time. But if you go to the precision farming equipment, which is already available, then we did this in arable farming, this research, then we noticed that they use GNSS systems to drive from A to B. So to have a straight line where they don't have to steer. So that's something which is a success, and close to 90% of the farmers, and at the moment it's more than 90%, I'm pretty sure, are using GNSS systems to drive in straight lines from A to B. They all have a isobus terminal, but most of them, well, 60%, so most of them know how to use it, but it's quite limited. And also the implements that make use of the isobus, so that you have a good connection with your tractor in your implement, and that they can also use each other's sensors for forces or driving straight lines. Yeah, that's limited used at the moment. And then when you even come to all the available tools that there are for precision farming, like variable rate applications for seeding, variable rate applications for nitrogen, variable rate application for fungicides and for herbicides, then we see a big drop that hardly any of these companies use this at the moment. So we started the project, which was quite successful, and that's why I also would like to point it up. So we tried to boost the uptake, and we had a program which is called National Field Lab of Precision Farming, where we took some farmers, and you see the map of the Netherlands with the farmers which were already joining that project. And around that farmer, he made a vlog, a video blog every week. He did it together with the Farmers Magazine, so it was also a collaboration on communication with the Farmers Magazine. And around that farmer, we also brought technicians that should integrate things for the farmer on that specific place, and also agronomists. So from research, from Wageningen, in most cases, not in all cases. We also had some private advisors connected to these farmers. And they also explain, to have a very open understanding from what is happening at the farm, how connected is his machinery to his farm management information system, to his implements. And I can tell you that our technical researchers need to do a lot. They expected that everything should be there, but connectivity between management information systems, tractor, implements, it was really poor. Decision support system. So there's still a lot that needs to be done to make it dedicated for every individual farmer. And it's very important that that there are people assisting these farmers in getting all these things running and also getting it in a very convenient way. So the systems were not convenient at all. But we managed. For example, what we did the first year was variable rate application on lime application, on soil herbicide, on nematode management, leaf desiccant, and also the top dress nitrogen, and also some plant density. So we started also with a limited number in the first year. The second year we scaled this up to do some complete route planning, not only A to B lines, but also the turning of the tractors, to do it always in the same way. And then also some precision irrigation, fungicide. So we added another 6. So you had already 12 precision farming applications. And in the last year, we added another 6. So they have now 8 precision agriculture applications available. And this was all communicated a lot, and it gave a big boost. So I think it's good to start this presentation with some uptake on how difficult it is to start with precision farming, but it's very important to start and to have as well an agronomist and a technician connected to you as a farmer, because you do not know everything, and it was very valuable to have these people aligned. So this was quite a successful project. People are still talking about this, that it helped them very much. Then a little deeper. So what are we doing in precision farming, and how does it work? So we constructed together with the machine manufacturer this weeding machine. And at first, that's already 12 to 15 years ago, this machine was only weeding and nothing else. But there are cameras under the booth, and but we do nothing with the data. So, but we take the image, then throw the image away, and we only use it to control our activators for weeding, and we do everything the same. Then the breeding companies came in and they told us, well, this is interesting. Can we also have the pictures, and can you also make a crop report for every crop? So from that moment on, we removed the weeding devices, so it looks easier. But under the booth with the cameras, we needed to do a lot more, because we needed to know where we are, to locate every individual crop, make multiple pictures every time we come back, and then also produce a time lapse, so that for the breeder, it's clear how these crops are growing, how many seeds came up, how homogeneous these crops are growing, so that they are equal to be harvested in all cases. And a breeder has many small fields, so we also had to register every small field and make a time lapse for a number of crops. We did not do this for all the crops, but for every field we took a few reference crops where we at least took a time lapse. So that's how we make this crop report. When the farmers saw this, they said, well, this is interesting. This is what we want as well, because now we can also detect our weeds and our crops. So that was the next stage, where also the farmers, you can see that this weeding machine is grown already a little bit. Now we have 12 cameras under the booth. We can do a wider range, but in the same time, at the moment, we also make a map on growth to predict harvest and to predict yields up front, so that the farmer already can start selling. and we also calculate where the weeds are in our fields. And of course, we also make some growth modeling based on this growth, because we measure also the yield. And that's another big task we do at the moment. On all our harvesters, we also mount sensors. So now we have the loop closed. So we have a loop where we grow, where we monitor growth, and where we can also see what is the actual harvest. So from year to year, we can learn much better. We know better when to harvest, what the ultimate timing is to harvest. In some cases, we only take parts of the harvest, so to leave the younger or the plants that are leaning back or are behind growth to harvest them later. We do the same with the weeds. So when weeding is very much affecting, we come back earlier, so we can also do better management. And we can also, and what we also learned is that also the farmer has to do some research. So what we also do with our management information systems is that we divide the field also in different plots, so that the farmer is also able to take different measures in different plots and try to learn from that. Also to learn what is the effect on weeding, because that is different for every crop, every variety, every soil, every situation. So also the farmer needs to adopt some research to continuously improve, and he now has this data available. At the same time, what we did is also made contracts for the machine manufacturer with the farmers, so that at least the machine manufacturer can also load the machine setting data for every machine which is in the field. And that's also being done. So for every 20 meters, a new setting is applied. All the settings are sent to the machine manufacturer. And so because the farmer still needs to adjust quite a lot before he can start weeding. And the ultimate goal is, he already now gives advice what the possible setting is, but eventually, based on what we have learned from other farmers, we should do these settings for the farmer automatically. So to also make it brilliant, simple to use for the farmer. So he just drives 20 meters, then drives back and starts the operation based on what the cameras have seen and how they have adjusted the actuators, the cameras, the illumination by itself. So we are not there yet, but that's the ultimate goal of what we would like to do. So let's go a little bit back to robotics. So if you look to the agroecology guys, girls, they are also very much into agroforestry and regenerative strip farming. What they always find out when you go to smaller fields, you need more labor. And all their concepts end most of the times with robots, because it's very difficult to go back. It's more sustainable, it's good for biodiversity, but it's not good for cost. So and I think that's but then the robots should do a lot. And if you look now to a combine harvester, that's a very complex machine. So we also think on possibilities where we can make robots easier. For example, not make a full factory on wheels, but for example only harvest the crop of the cereals and do the processing of these cereals later in a controlled environment, so that you do not need a very heavy machine, and you can also you can make the machine much easier and more ready for robotics. So this is an example of what they did with a Chinese harvester to make it autonomous, and that's a very simple harvester. Because robots are the future, robots can reach every plant, every animal, everywhere. It can act more frequent and collect reproducible data. It can perform good in repetitive short cycle tasks. It can introduce new protection methods like plasma and UVC treatment. UVC treatment, for example, is very effective on fungi in your crop. But yeah, to do it properly and not to kill your target crop, so to say, you have to come back every 2 or 3 days with a small doses. So and yeah, only a robot can do that, because if you need to do that manually, it will be way too expensive. So it's important to act more precise at the right timing, because then you reduce also soil compaction, chemicals, water, fertilizers of manure, energy, labor, administration, also very important when all data is automated, loaded and registered and made ready for your government or whatever. It also reduces risks, logistics, and can also replace harsh working conditions. So it makes life easier. That's at least the ultimate goal, and potentially I think it's also there, but there's still a long way to go. And I think if you have robots, then it's also easier to scale, and then it's also, you can bring also food production closer to urban societies, and you don't have to source your labor and your logistics from very far away. So it will be the future, but we are not there yet. Some examples what we are doing in Wageningen, that is that I think all major tractors are prepared for autonomous driving. It's just that they don't have it, but we are building setups in the top rights. You can build on a tractor, and then you can do autonomous driving. And if a farmer combines these kits together with a tractor, and then he takes over responsibility, and he can do this. So also already at the moment commercially available. Then you have these master-slave operations, which is also used in big agricultural sites like the US or Australia. Then you have these lawn mowers on a little bigger level for golf courses, which is also commercially available. And then we also work on the electrification of robots. This is what we do together with the Korean Institute, where we also make some safety measures. What we have learned from all these robots is, so driving is quite easy, but it's still not fully unsupervised. So you need a groundsman that takes care about safety, closes fences, and then also the whole combination with power packs is also very difficult. So I visualized it here. So if you would like to use robots, then you have a task in mind. So that's your first step. You know that you need an implement and a robot or power pack. That's the first hurdle, because do they speak to each other? Are they good connected? Is your implement ready for this? Even a simple plow, for example, if it does not have any sensors, how does a robot know how to pull? And when you are going on slopes, should you lift the plow a little bit? So, and are you satisfied about the outcome of your plow? So about the task he already did. So you need good communication between your implement and your robot. And a plow immediately needs a lot of sensors to lift, to feel forces, to evaluate on the quality of your operation. And if there is an obstacle, for example, all these kind of things that is required to sense if a robot can do an operation. I think that's still the missing thing. The implement should do the thing, but most implements at the moment are just copies of what we all have, and that's not smart enough. Then if you have this combined that works, then you should set out a task plan, and that task and a full task plan. So even the turning, everything should be there, and then you can simulate the task plan. And if you are satisfied, then you can execute. And also building these task plan and simulation of these task plan are at the moment not convenient yet. So we need to do something there as well. So what is still missing in robotics is that we do not have level 5 certified safety systems. So it's not very safe at the moment still. Though there are now robots starting to come close to implementation in practice unsupervised, because at the moment all robots are more or less supervised. So you need someone that takes a look at this robot, which do not save you any labor. If that's your goal, then you are not very handy. Safe geofencing is not always safe. Local connectivity, that's something you can organize. Also real-time tracking. Teleoperation of your robot is possible, but connectivity could be built on the farm side, but in most cases it's not there. But you also would like to take over remote control of your robots. So especially when robots are on fields on hundreds of or meters away, you would like to look with your robot, how is he doing? You would like to see that on your smartphone or tablet. And you also would like to take over if a robot comes into error. Then you would like to help him. So the whole error handling, remote assistance is poorly developed at the moment with most robots. Also, the whole implement behavior already mentioned, it is also poorly developed. Task quality feedback, not in place yet. Unsupervised learnings that you can learn throughout the season, not in place. So also the whole interoperability with the farm management information system could be done, but is still poor developed, and it's also not convenient. So at the moment we are still facing some issues. We also test and validate a lot of robots for other machineries. So that's what we also do. And here you see some examples of robots what we have already investigated. You see some weeding robots, some tillage, and also some autonomous agriculture. Then, on autonomous navigation for agriculture, we advise that there's still poor implementation and validation of robots. And there's limited durable examples in open field, and they are not convenient or brilliant, simple to use. There's limited implement support, poor connectivity, plan, simulate, execute, still not there. And I asked one of the researchers who's working a lot with these robots, and he said, well, autonomous driving in agriculture is easy. Most robots focus on that and they are successful, but it's still not safe enough. There are hardly any smart implements. Farmers need to work more precise with GNSS, and the AB lines is not enough. So also the farmer need to grow in this domain as well. And no quality of task feedback options. And the researcher said I never leave the machine. In the future, it's more a cobot or teleoperated robot. Perhaps that should be the way to go. And I think also teleoperation could be an option. An AB line in most cases is fine. Teleoperation is a lot used in mining. And I also discussed this with the big six, the John Deere, the CNH, Echo, Kubota, and they also think that teleoperation could be a way to go, and then a teleoperator could perhaps handle multiple robots on different fields. So that's a possibility that we will definitely explore in the future, and you can also do it as a service. Then a little bit about digital twinning on farms. So in the top left, you see a farm management information system. And we are now about to take the step to a 3D management information system. So to really scan farm premises, and we can do this, for example, with a laser together with a 360 color image, and then hopefully in the future we can more go to gaming-like domains where we can set out operations not only in the fields but also between farm premises and the field, so that you can also drive on the farm premises in and out of a stable to bring feed to the cows, for example. But to be able to do that, you need quite quickly a clear 3D environment where you can operate and where all obstacles are. And we are now also making tooling for that, so that it is possible to make 3D environments to enable robotic operations. So that's the digital twin for robotic operations. There's also a digital twin possible for growing. So that's a complete different field. We also work on that as well. In Wageningen, we have also now one greenhouse in a full digital twin. So on the left side, you see a growth model represented in a 3D image. And that growth model already works with the shade interception by the construction, a sun that goes over the greenhouse. It even takes into account when crops are standing close to each other and you have more light interceptions. This is all calculated by a real 3D environment and these crops grow also digitally. But the only problem is it's never ideal. So we make big mistakes, and if we make mistakes at the beginning, it extrapolates in the future. So you need in between recalibrations so that you can also adopt. But it is already sensitive for light, CO2, water use, and so all these things are already into the growth model. And now we are about to also make these recalibrations. So on the right hand side, you see the real crop, and we also, this is a full greenhouse where we can move every individual plot. So for the robotic operation, that's already fully established, but not on the growth. And now we are trying to make the next step, also to make these 3D images and connect these 3D images, find the plant again, plot them over your growth model, and also recalibrate your growth model so that you have a continuously update on what to expect on growth. And I think these kind of measures, we also now have granted our first project in the open field. So this is in the greenhouse, but we will also start to do this in the open field so that we can really model in time the crop and predict a better harvest, or even a stress. When the crop is not growing as expected, then probably there's a stress, and then it's valuable to look what is happening there. And this is also an example how we make 3D images. So this is really this is a real plant, by the way, but then image with multiple cameras. You can see it also in the small video on the right hand side, where we look with 10 cameras to every plant and make the image from every 10 cameras on the same time. And then we can make a full 3D reconstruction of the plant and also calculate the real leaf area. And the nice thing is that you can also control robots with that. So if you have the full 3D information of these plants, you can also use this for example, genetic sampling. So many breeders have this genetic sampler already in use. And you can also use it for some cuttings. Some other projects on robotics we do. You see here the planting of lid cactus, also planting of chrysanthemum cuttings. You have already autonomous vehicles in the greenhouse running. So these are all three available. The bottom left, that's automated harvesting of roses. That's still not commercially viable. We had quite some success, so we harvested more than 90% of all the ripe roses. So we follow from top to bottom the rows to the cutting point. We did this trial 24/7, 4 months long. So it was a very expensive trial, so to say, because you need people in that area full time, the clock around. And but yeah, the machine manufacturer became bankrupt, and all the moving row systems, roses are now coming from East African countries mostly. So other markets took over, and now it's not possible. So now we're still looking for a client to finish this project off. Something about another digital twin. So you have a digital twin about the big operations to set out robots, vehicles, but you also would like to use digital twins for testing harvest operations, for example. So what we did, we built also the plants in 3D. So this is some sweet peppers imaged in 3D, and then also mounted it back into a digital plant. So we have drawn these leaves also ourselves. And so now we are able to make also digital 3D plants. And we have even built a randomizer so that you can, based on the breeder information, you can produce digital plants. And that's very handy if you would like to check what is the best camera position to have the biggest chance that you will see sweet peppers in the best situation. So also you can also do cycle tests of your robots. So we did a lot of, and we built complete greenhouses with these plants. So this is an example of a plant in a greenhouse, and we know every single component. That's why I use this image. We know what a sweet pepper is, and a leaf, and a nerve, and a stem, and a wire. So all these components are clear. And on the left hand side, you see one of these artificial sweet pepper plants. So we have drawn it ourselves, so it's not existing in reality. On the right hand side, you see a real tomato plant. And what we did is we tried to learn from each other, from one to another, and that's what we also did. You can see it in the next slide, I hope. But it works, yes. So initially on the left hand side, we knew everything, and with deep learning, so we also found all these objects on the right hand side. So without doing any other programming, but just tell the other pictures that it is possible to find it in the other picture in the real world as well, we are able to find also these different sweet peppers in the real world, and also start robotic operations. So that's what we also did in our next slide. This is another example. This is also where we also used the camera to control the robot. So you see the camera in the end effector, or in the hand of the robot, and the end effector is at the moment looking to these sweet peppers, and it can quite quickly find these robots. So it was quite a success, and it makes also robotics to the most easy form, because if you now look, you can build everything in the head of the robot, and you just use a normal industrial manipulator, and it should do the job himself. And that's what we also did in our sweet pepper harvester, which we tested in the greenhouse farm. So now the robot is only this top thing, and it gives a cut. It has the camera sensors in it. It has illumination to give extra light to the system, and it also can grab the crop. And this robot is standing on the same spot where normally a human should stand. So and if you look to all the materials that are in the mechanical components and the camera systems, that's not even 5,000 euros, so to say. But it's also not very expensive. Then it's I must say it's still very difficult to go from 100% manual operations to 100% robotic operations. So this is a nice example where we also try let the robot do the easy tasks and let the human do the rest. And I think that's also a very good way to go to to enable robotic operations. I see too many projects where we try to do everything, and when we are doing only 80%, the farmer is not satisfied. But I think if you are doing 80%, you might have already a good business case, or perhaps even with 50%. And I think we should explore these directions much more when you have a human working together with a robot, because in this case you could already save the first 50% of your labor force. So we are continuing this project. This is an example of 2 years ago, when it was still open research. Programming is also becoming a little bit more easier. You do not have to program everything. So this is a nice example of learning by demonstration. So you see my colleague harvesting apples, and that is registered by a set of cameras. And eventually you give also that same task to the robot. You say, well, do the same as what I did with my hand. And now also the robot here is able to find these apples. And this is supervised, but you could also imagine that you could train unsupervised, and that's also the next way to go. So because a robot knows when it did a success, because he could have sensors in his end effector, and then also give that feedback back to the robot. So this was a success. Remember this one, and if he did not had a success, then he should also learn from do not this ever again. And so this is also how you can train. And yeah, hopefully eventually we could even monitor how humans do it in reality, and perhaps even can take the learnings from that as well. Then what we also use a little bit on the precision agriculture and disease detection and the whole monitoring, because that's also a big domain for robotics, is that we look to yield and quality first. I think that's the biggest demand at the moment, where we see also the best viable business cases. Then look at stress, for example, to photosynthesis or growth that is behind, and then determine the disease. So that's in most cases the 3 steps we follow. And these are a few examples, which are, the bottom 2 are both already commercially available and built for to predict the harvest in a better way, and also to predict ripeness and the actual quality which is hanging there. You could also evaluate workers for this, for example. The top 2 are more using for breeding purposes. And on the top right, you see a very big flash, and that's how we measure photosynthesis with chlorophyll fluorescence, which is also a method to know to measure photosynthesis. I also have an example for that. This is how does photosynthesis looks like if you use this camera system. You can easily see how diseases are growing into a potato leaf. This is normal stress, what you will notice in the plants. This is the ripening of roses, and this is the ripening of strawberries, what you could use. So this is what is already working, but not commercially available. Yeah, it is used in research a lot, these methods, but I did not see yet commercial applications in practice. So I'm wondering how long that could take, but I think it's potentially a very interesting method. Yeah, but I think this was it. Hopefully you learned something.